Hello, Tim McKeskey here. I'm going to be doing a lot of this brief video on Excel just to demonstrate some different kinds of decay. Now, in the context of acoustics, the kind of decay I'm talking about is what happens to vibrations. And so it will relate to the first few labs because the mass and spring lab and the pendulum both exhibit the kind of decay I'm going to talk about. Or if you want something more explicitly acoustics, the dying away of a tuning fork sound might obey this kind of behavior. So by decay, I just mean we want to formalize how the amplitude or size of a vibration goes down over time. And there is a way we typically discuss that trend. The first thing I'm going to do is describe what the decay is not. So let me share my Excel spreadsheet with you here. Okay, so here we are. This is an example of what I would call a linear decay. So in this case, I'm picturing amplitude, right? You see in my graph, it says amplitude in centimeters. So that might be for the mass spring lab we start with the maximum distance between the, where the mass is located and the equilibrium point, or the center of the vibration. It's that distance. So an amplitude is a way of giving the size of the motion. So if a mass goes from low to high, the amplitude would be half of that distance. And because of various factors that exist in the world, in the real world, these vibrations or oscillations might decay. This is the way that it will not happen in a lab, but I want to show you what I mean when I call it linear decay. So the way I made up these numbers is I thought to myself, okay, what if when we start the motion, the amplitude is 10 centimeters, it's about 4 inches. It's a little big for the lab, but certainly we could do it in some cases. Right, let's say the amplitude is about 10 centimeters. And what a linear decay would mean is that after every amount of time, in this case it's 20 seconds, the amplitude goes down by 2. So after 20 seconds, the amplitude is 8. After 40 seconds, the amplitude is 6. After 60 seconds, the amplitude is 4, and so on. And if I were to plot this on a simple scatter plot here, what you're going to get once the pinwheel of death is done, right? You get a plot that looks something like this, which is simply a straight line down. Right, and what that implies is, right, if you let enough time pass, the amplitude will be 0. There'll be no more vibration after that point. And in real life situations involving like masses and springs and pendulums and things like this, you eventually always do reach a point where the motion stops, but the way that decay actually happens in nature takes a little bit longer. So this is linear decay, and it's so called because, right, it's a straight line. If I draw a trend line, you see that all the data points fall along a straight line, and so on. So for more details on how I'm doing the plotting, I have a separate video when we get to some lab techniques. I just wanted to explain the concept of decay half-time as you'll see it in the course. So this, right, I'm going to construct a graph showing what's called exponential decay, and this is more like how these systems behave in the real world. So for linear decay, I lost the same number of centimeters every 20 seconds. But here, I want to make a spreadsheet showing what happens when the decay half-time is 20 seconds. So decay half-time equals 20 seconds means after 20 seconds, the amplitude is cut in half. Pretty simple. I'm not even going to use a calculator for the first couple. So, right, if at the start of my motion, the amplitude is 10 centimeters, decay half time equals 20 seconds means that after 20 seconds, the amplitude is cut in half, so half of 10 is 5. Then after another 20 seconds, so from 20 to 40, the amplitude's cut in half again, which is 2.5. And then after another 20 seconds, the amplitude is cut in half again, 1.25. And after 20 seconds, it's cut in half again. I think I can do this. See, what is that? That would be, well, I think it's 0.6125, but why not get it right? Oh, 0.625. All right, that's better. Yep. One digit off. So I might as well make the computer do the math for me. I take what it was 20 seconds ago and divide by 2. And it looks like that. And you notice the numbers are still getting smaller, but the steps aren't equal size. It's like the smaller your amplitude is, the less decaying is possible. Okay, so this is what a decay half time looks like. A decay half time pattern looks like, and it's also something that's called exponential decay. And you can see the difference if I plot these points. Instead of them existing on a straight line, we have an exponential decay is what that's called, which means the function that would fit it is something that's called an exponential function. So it involves an exponent or a power. And Excel sometimes even knows how to do something like that. Like when I first ask it to do a trend line, it assumes I want a straight line, and a straight line does a bad job of showing that data off. But if I switch it to what's called an exponential, then very, very easy for it to handle that. I can even, if I want to, I'm showing this off here, I can make the computer in this case tell me what the equation is, and trying to get the size a little better. It's not vitally important that you see all the details, but I want to make this big enough. In this case, we have this 10 times e to the some power times x, and that's one way of writing an exponential function. We don't have to use the base e in our power here, but it's one example of an exponential function. And rather than understanding what exactly that constant e means, in this course, I'm usually going to refer to these decays by the decay half time. So the value of the graph on the y-axis is cut in half when the decay half time passes. It doesn't have to be 0 to 20, 20 to 40, 40 to 60 either. If you look at where the graph is at like 10 seconds, see it's a little above 7, and at 30 seconds it's below 4 a little bit. So that factor of 1/2 applies just equally well there. All right. Now, to show you another one of these, I'm going to paste my data. Okay, and I'll plot it again. Same kind of scatter chart. This is the same chart that I generated before. If I make the decay half time 10 seconds now, right? I can do that, and Excel will automatically fix the points for me. Okay. I get the exact same shape as before, same shape, except the decay happens more and more quickly. So in this case, we only need 10 seconds for the graph to drop by half. So in this case, I'd say the decay half time equals 10 seconds, and that's it. Mathematically, what this pattern represents elsewhere in nature, it's like the concept of radioactive half-life, if you've ever heard of that. What half-life refers to is if you have a radioactive substance and you know what its half-life is, the half-life is the amount of time it takes for half of the substance to decay to something else. So one of the most common ones used in dating is a carbon-14 isotope whose half-life is on the order of 5,000, 6,000 years, something like this. So if you have a quantity of carbon-14 and that many years passes afterwards, you're going to have half of that left. In this case, I'm not talking about an amount of substance, but rather the amplitude of a vibration, and that's the pattern. So in a question, I'll either tell you the decay half-time and you have to continue the pattern forward, or after every half-time period, the amplitude is cut in half, or I'll give you a table and you have to determine just from the data points, find two where one is half of the other and how long did that take? That would be the decay half-time. So those would be some questions I could ask. So I hope you see the difference. In simple harmonic motion, which includes things like vibrating tuning forks or the mass spring experiment or the pendulum experiment, we have what's called exponential decay, and a way of describing that is using the decay half-time. That's all. So I will end there.